Welcome back, everyone. So today in this video, you're going to be learning about light. What kind of wave is it? What are some properties that are important about it? And how to basically navigate this general idea of light. So firstly, light is an electromagnetic transverse wave. So remember, transverse looks like this. Okay, so it's where the wave's particles vibrate perpendicular to the wave's velocity. So as light travels this way, its particles will vibrate up and down. Now, the electromagnetic side of it means that it can travel in a vacuum. It does not need a medium, right? Which is good because space is mostly a vacuum, and if light couldn't travel in a vacuum, then light would never reach Earth from the sun. Now, light is important because of one major thing about it, and that is the speed of light. And the speed of light is this. We use the symbol c, a lowercase c, for the speed of light. I don't really know why. It's just, it makes it a special value. Equals 3 times 10 to the 8 meters per second. Or in other words, 300 million meters per second. Okay, now that's an approximation. It's really like 299 million, blah, blah, there's a lot more numbers to it. But we round up, and we can just say 3 times 10 to the 8 meters per second. Right? And it's symbolized by this value c. Now, that value, this value c, 3 times 10 to the 8 meters per second, is true in a vacuum. Okay? In another video, when we talk about refraction, you'll see that light can slow down. It can never be faster than this 3 times 10 to the 8 meters per second, though. If you ever see a question and one of the choices is like 3.6 times 10 to the 8 meters per second, that can't be right. It's impossible for that to be right. Now, light works on a spectrum. Okay, light works on a spectrum. Now, that spectrum, no matter what, still follows this equation, right? So this is c for our speed of light. So that could also be a v, right? You've seen v equals lambda times frequency. In this case, we're talking specifically about light. So everything you're about to see with this spectrum follows this c equals v, or f times lambda. Okay, so everything that you're about to hear, and I've got a little diagram I'm going to show you, talks about the different types of the spectrum, still follows that equation. Now, like I said, light works on a spectrum. Okay, so that looks like this. Okay, this is the same picture as on page 2 of your reference tables, so you'll be able to take a look at that. Now, from here all the way to here, right, we follow different ranges of the electromagnetic spectrum. Down over on this end are gamma rays. Okay, they have wavelengths, that's these top set of numbers, your wavelengths, of 10 to the minus 13 meters, which means basically if you were to take a single meter stick and split it up into 10 trillion different pieces, or equal sized pieces, one of those pieces would be the wavelength of a gamma ray. Okay, down on the bottom we have our frequencies. So a gamma ray has a wavelength, as you see up here, times 10 to the negative 13, and down here has a frequency of times 10 to the 21. So very low wavelength, very short wavelength, very high frequency. Okay, as you go this way, your wavelength starts to increase and your frequency starts to decrease. So for example, over here are your radio waves, okay, which is another thing we're going to get to in a little bit. Your radio waves can have wavelengths on the order of 10 to the 4, 1 times 10 to the 4, which is 10,000 meters, right? So basically you have 1 trillionth of 1 meter all the way up to over 6 miles for just one wavelength, right? And it's all light. Now, remember how we were talking about, we said c, or velocity, equals wavelength times frequency, right? No matter which two sets of numbers that you put together, right, for each chunk, it's going to work out that the speed is 3 times 10 to the 8 meters per second. So as your wavelength increases, your frequency decreases at the ratio of 3 times 10 to the 8 meters per second. Now, I want to just talk about different parts of these ranges here, right? So over here we have our gamma rays. Okay, gamma rays can be produced here on Earth. Typically, they're more produced in a lab. They're not really overly naturally produced. Sometimes, you know, if an element decays, that goes away. They're mostly produced in space. Okay, which is good because they're very, very, very dangerous. They're not going to turn you into the Hulk. They can make you very sick very quickly, and they're not good. Luckily, any gamma rays that are produced in space, our magnetic field, our planet's magnetic field, does a good job of kind of shooting away. Okay? As we go down further and further, right, we're getting to X-rays, which is here. Again, you can follow along in your reference tables, right? We obviously use X-rays for medical purposes, among other things. Then we get to ultraviolet, right? It's all a spectrum, right? So you see some of this overlap. Then we get to ultraviolet, right? We know ultraviolet can be a bit dangerous because it can give people skin cancer, which is why it's important to always wear sunscreen or hats, sunglasses, that kind of stuff. It can cause cataracts in your eyes. Right? Then we get into visible light. Now, if you notice, visible light, very, very, very tiny little section of this whole big spectrum. Remember, we're talking about on the order of 1/1,000,000th of a meter all the way up to 6 miles for just one wave. Right? So this tiny, tiny, tiny little section, that's all we can see. Right? So here we have violet, higher frequency, lower wavelength, all the way up to red, which would be lower frequency, higher wavelength. Okay, so this is all we can see right here. Now, in this chart, right, these numbers down here represent the ranges for each of these colors. Right, so you'll see the range of violet, for example, is 7.69 times 10 to the 14 hertz, all the way to 6.59 times 10 to the 14 hertz. Right, these are frequencies down here, and so on and so forth. Right, so if you ever saw a question and they gave you, oh, what is a frequency? See if it falls in there first, and then you might be able to locate a color or something like that. Then we get to infrared. Right, infrared is responsible for heat. Right, every human being, every living thing radiates heat, which is measured in the infrared part of the spectrum. Right, if you've ever seen movies like they've got their heat vision goggles or whatever, they're measuring the heat off of living beings. Right, then we have microwaves. Now, you know, I'm sure you think microwaves, ooh, let me heat up this Hot Pocket or something. Well, microwaves do that. They have in your microwave oven, but they're also in the range where you have your cell phone signals, your Wi-Fi, things like that, right? Then we get into radio waves. Now, that's the key thing here. Radio waves are light waves, right? That's a very common mistake that people make. They say, wait a second. All right, so I listen to the radio, so radio waves must be sound waves. Well, no. Okay? The radio tower from the radio station emits an electromagnetic wave in this part of the spectrum that is then picked up via resonance by your antenna. The antenna then vibrates at that frequency, which sends a signal to the electronics in the radio set that then converts that signal into a sound wave, right? But radio waves are light waves. So if you see a question where it's like, oh, a radio wave has a frequency of, you know, 4.6 times 10 to the 6 hertz or something, right? What is the wavelength? Well, you'll say, you'll use the speed of light, c, equals your frequency times that wavelength. And then you can solve for what you need. Okay? Now, over here are what's called ionizing radiation, which means that it has enough energy to pop electrons off of their atoms, out of their orbits. Right? That can be very dangerous to human health. Right? That's why when you get x-rays at the dentist, they put that big lead blanket on top of you, or you want to try to limit how much exposure you have to x-ray radiation or to ultraviolet. Again, that's why you want hats, sunglasses, sunscreen, that kind of stuff, right? To help protect you from this. Obviously, the more energetic you get, the more dangerous it can be. Once you get kind of like here, the back end of ultraviolet and over this way, that's called non-ionizing radiation, which means it doesn't have enough energy to pop electrons off of their orbits, out of their orbits. Right? They still could pose some health risks depending on how long and what the intensity is of your exposure. Like if you're exposed to too many infrared waves for too long of a time, you get overheated, right? And which can obviously cause its own health issues. Same thing with microwaves. Your microwave oven, it's got that kind of mesh on the door. You're okay from that. we're talking about really high intensity things. You might get overheated, and that could cause some chemical issues there. But otherwise, generally okay. All right, so that's pretty much it for light. The key thing here is to know that that speed of light, 3 times 10 to the 8 meters per second, is constant for all of those types of light waves in a vacuum. It still follows that V equals lambda times frequency, wavelength times frequency, so you'll be able to find that ratio there if need be. And radio waves are light waves. Those are the probably 3-4 biggest things I could say about light. All right, so that's all I got for that for today. Until next time, I'll see you later.